what we are going to discuss now are Kafka basics, right? So we have numerous concepts. Like earlier, we have discussed about topics, partitions, right, and what are producers and consumers. But what builds these, right? What are the building blocks of Kafka? So we have brokers, zookeepers, and how these partitions are getting replicated across brokers, right, and how partition leader is elected or how broker election is performed or what are zookeepers, right? We are going to discuss all of them now. So let's just get into details. Brokers. So what brokers are? As I have discussed, brokers are nothing but servers or the machines. It can be Linux machines, Windows machines, right, on which Kafka servers are hosted. So we have different functionalities of brokers, like as you can see, controller election, Kafka servers. I mean, what Kafka servers are we going to discuss, and controller, what controller does, and message queuing, managing partitions, right? Brokers manages the partitions, and metadata management, right? So first, Kafka servers. So Kafka servers have data storage blocks that are appended to it or that are tagged to it. Brokers. Now we are going to discuss about what brokers are. Brokers are nothing but a Linux or Windows or any operating system machine on which Kafka servers are hosted. So these brokers are responsible for hosting the topics or managing the partitions and consisting different configuration details of metadata such as topics or where topic partitions are and what are the different replicas of it, right? These are several functionalities of brokers. So first, let's discuss about Kafka servers. So every Kafka server is mounted with certain storage, right? If it's Windows, we have file system, and Linux, we can have, right? We have the internal storage, and if you take EC2, we have EBS, EFS storage, and different types of data storages. So Kafka use these storages to store different data, right? Of topic, they are called, we have messages. So messages are stored in this data storage and accessed by consumers when they require, right? This is about Kafka servers. And next coming to controller election, right? So one of the brokers initiate the election during startup. Why this election is? Because of course we have numerous brokers, let's say three or five or any odd number of brokers, right? So we require odd number of brokers because we can't have even number of votes. We need at least a majority, right? This is similar to how assembly elections are done. We require a majority. So one of the brokers initiate the election during startup. So this election process involves coordination among all the brokers in the cluster, and it's heavily reliable on Zookeeper, right? So when the cluster starts up, each broker emits a controller event, an event to demonstrate that it's starting the election, right, and initiates the election. So each broker nominates itself to be a potential controller and registered it, and it registers the Zookeeper in older versions, of course. We are moving away from Zookeeper and its dependency, and we are introducing craft mode, and we are going to discuss in the later part of this video, right? And the first broker to create this temporary node, or we call a Z node in this Zookeeper, becomes a controller, and this gets a controller epoch, right? So this is how controllers are, sorry, not controllers, controller. At a time, only a single broker can be controller among any number of brokers, right? This is how controller election is done. And coming to controller, what are its different functionalities or what are its responsibilities? As we have discussed, only one controller can exist for any number of brokers, and we have controller is responsible for partition leader election, right? We have replicas for partitions, and each replica is located at different brokers, right? But of among these partitions, let's say a partition have three replicas, right? Out of these three replicas, one should be a leader and the remaining will be followers. So this partition leader election is controlled by Controller, right? So when a broker goes offline or a new topic is created, the controller determines which broker should be the leader for each partition and it initiates leader elections accordingly, right? And next we have partition reassignment. If the cluster undergoes changes, such as broker additions, like broker can add or we can remove a broker, right? Or if the partition replicas need to be rebalanced for better resource utilization, the controller handles this partition reassignment process. Next, we have broker failure handling. So, in case of the broker failures, right, the controller detects the failures and takes the required actions, such as like initiating the leader elections, right, or partition reassignment to the healthy brokers. This is one of the functionalities of broker failure handling. So, cluster-wide configuration management. The controller ensures that cluster-wide configurations like topic configurations or broker configurations that are propagated to all brokers in the cluster. And also we have Zookeepers interaction. So in earlier versions of Kafka, the controller used Zookeeper for coordination and distributed locking. However, in newer versions, Kafka has moved away from direct Zookeeper dependency for most operations related to controller. But yeah, Zookeeper is still used for storing metadata. Starting from Kafka 3.3.1, we have production ready craft modes. So we will discuss about that as well, right? And this is about controller and coming to messages queuing, right? So brokers queue the incoming messages, right? Producers produce the messages and puts them to brokers, but these are directly not consumed by the consumers, right? The brokers go through a queue, and this queue mechanism ensures that messages are efficiently processed and delivered to the end consumers, right? And managing partitions, of course, we have discussed, right? Later partitions and the followers, how we distributed data among it, and metadata management as well. And it has different topic configurations or crucial metadata about partitions and consumer offsets, of course, right? This metadata is vital for routing the messages and maintaining the cluster integrity. And next, we have zookeepers. So, what exactly is a zookeeper? So Kafka is managed by an external service, right? This is called Zookeeper. Zookeeper is not just a single one. We have an ensemble. Ensemble is nothing but a group of servers, right? Yep. Kafka is managed by Zookeeper servers, ensemble, right? So each server maintains an in-memory image. So what is a Zookeeper, right? So Zookeeper is nothing but a group of servers that manages Kafka, right? Each Zookeeper server maintains an in-memory image of the state in a persistent store, like whatever the store it maintains, right? Either DB or disk or anything. Not DB. Each Zookeeper server maintains an in-memory image of the state in its store, in its data store to be precise, right? As we know, only one broker will be the controller in the cluster, and this controller is also elected by a Zookeeper ensemble, if you remember, right? This is a part of controller election, right? How it registers with the Zookeeper and how a leader is elected, right? So next, how a Zookeeper, you know, stores the data. It's crucial for, for efficient data management. Hierarchical namespace. So similar to our file system, right? How we store our files, we create a folder and inside that folder we have multiple folders or files, right? So similarly, we have Z nodes, or Zookeeper nodes, which are similar to folders, right? And inside that folder, we could have, like we have folders and files. Zookeeper organizes data with nodes instead of folders. We have hierarchical namespace. So Zookeeper organizes the data in a hierarchical namespace that is similar to a file system. We create a folder, and inside that, of course, we could have other folders or files, right? Similarly, Zookeeper organizes data with the nodes instead of folders. Nodes can have children, like having other folders and files, and each node has a unique name, right? We can have the nodes representing different parts of the system. like the status information or configuration settings and many more. By organizing them this way, it allows Zookeeper to locate and manage these pieces easily, right? And we have discussed controller election, right? So how this controller is elected, it's essential in electing the controller, right? Brokers try to create a temporary node in the Zookeeper, and the first one to create that will be the active controller. And next comes broker membership, right? When a broker connects to the Zookeeper, like a temporary Z node or an app of broker membership, right? When a broker connects to a Zookeeper, it creates a temporary node, right? We call it as ephemeral nodes, and these nodes cannot have children as the persistent nodes like folders and files, right? So these are just single nodes and is created under a group Z node. So when a brokers become inactive, this temporary Z node is removed from the group. So this is how it maintains the broker membership. What are the active brokers and not, right? And we have metadata management. So it stores different topic configs and ACLs, right? Access control lists. These control the access to a topic. So what users should access and what users can update or create or delete, right? All these are controlled by ACLs. And partition leadership info. So what is the partition leader and where the partition leader exactly resides, right? All this information is present with Zookeepers. And next we have craft mode. So craft mode is the way we are getting rid of Zookeeper, right? The dependency of Zookeeper. So we are replacing the Zookeeper with craft mode and it's production ready from 3.3.1, right? So next we have craft mode. What is a craft mode? So Kafka's architecture has been, highly dependent on Zookeeper, which is a separately managed group of servers, right? They have separate properties and separate everything. Itself, it's a system. So it's difficult to manage it or monitor or keep track of the health of it. So we need to have an additional, resources to manage it. So that is why we are moving away from Zookeeper architecture and to a quorum based controller, right, that uses an event source based implementation along with the raft consensus protocol, so kraft, right. This shift will completely remove the dependency on Zookeeper for cluster operations and management. Older versions of Kafka, right, do not support craft mode, and users must upgrade the client versions, of course, right, for craft mode. So and the latest versions support this and they are marked for production ready. Of course, craft mode is more scalable and eliminates the complexity that comes with the Zookeeper. It's highly scalable and provides high throughput, right? So this is about Zookeepers, and we are gonna have a separate discussion on craft mode. We are gonna have a separate discussion on what a craft mode is, right? So it's a huge concept. So it will we will discuss in the later videos. What do we have next? The replication. We have discussed about partition replication, right? Topic replication, the data. So how that data is replicated. So partition leader election. When we create a leader, when we create a topic, we define the number of partitions and the number of replicas. So any one of the partitions replicas. So if we have three replicas, that means we have one partitions copied to three. When we replication, right? So we have discussed a lot about like how topics are created or how this data is replicated again. So, replication. What exactly is replication? So we have discussed, right, what topics does and how data is. So, replication. What exactly is replication? Right, we know when we create a topic, we give the replication factor and the number of partitions, and this data is replicated among brokers. But how this is done, right? So when we create a topic, we define the partitions and the number of replicas. So if we say we want three replicas, so each partition will be copied to three brokers, right? So any one of the partitions among the replicas can be a leader, and the remaining will be the followers. So when the data is written to a leader partition, so it will copy the data asynchronously to the replicas, so that when the leader replicas go down, we can another in-sync replicas can come in as leaders, and consumers can seamlessly consume from that partition, right? So partition leader election. So when a topic is created or when a broker fails, Kafka initiates a leader election process to select a new leader for each partition. So this ensures that there is always a leader available for each partition. Asynchronous replication to followers. Right. So once the leader for each partition is elected, it replicates its data to the follower replicas. This replication is performed asynchronously, right? Meaning that the leader doesn't wait. It doesn't need the acknowledgement from followers before acknowledging the right to the producer, right? So there is a property like X, if you ACKS. So this is a property like how many acknowledgements are required. You just require the acknowledgement of the leader, or you require the acknowledgement from all the replicas, in sync replicas, right? This is a property within the producer. This we are going to discuss when we are doing hands-on with producers and consumers, right? So we have in sync replicas. What in sync replicas are? So Kafka maintains a set of replicas for each partition, right? In sync replicas, they should always be in sync with the leader. So these are the replicas that are fully caught up with the leader, as sync means. So only the replicas in the in-sync replicas are eligible to become leaders if the current leader fails. So let's say if there is a failure scenario and the leader goes down, and the remaining replicas within the ISR becomes the leaders. So there is a property unclean leader election, right? We can select the replica which is not in sync as the leader, where this is the case where we would need to. So there is also a property that defines. There is also a property within the topic where we can choose the replica which is not in sync to become the leader, right? So even if all the in sync replicas goes down, the replica which is not in sync can become the leader. But we could have data loss because we will not be sure like if data is synced with the replica which is not in sync, right? So this ensures that only replicas with the latest data can take over leadership. We can only enable that property of unclean replica election only if the data is, if we can only choose we can only choose to select the replica which is not in sync to be the leader when data can be missed, right? We can afford a data sap, right? So this is how in sync replicas are worked, and we have in sync up in failure scenarios, right? So if we have a failure and the replica or the in sync replica comes again, so it can catch up with the leader replica and sync the data with it. So we have fault tolerance. If the broker hosting a leader replica fails, one of the in sync replica follower of course becomes a new leader. So this process ensures that the system becomes fault tolerant and data is available even in the presence of broker failures. So This is how brokers, zookeepers, and replication of data works together to make the Kafka system more scalable, fault tolerant, and provide a high throughput, right? So that's it. See you soon.